Welcome back. This is Chapter 9. This is Section 9-5. This is recording number 1. So let's take a look at the table of contents here. What we've done up until now is we talked about testing the means. We had two ways of doing it, Z and T, if they were independent samples. So that's testing the means. There's a third way of doing the means, and that is for the situation where the samples are dependent. So for example, some sort of a matched pair, a before or after type of a situation. Then we talked about testing the proportion, the differences between proportions. So that's what percentage of the people get sick with or without a vaccine, that sort of thing. Finally, we're going to do section 9.5. So this is testing the difference between two variances. Now remember, variances, that's a measure of dispersion. How spread apart are you? How far apart are you? How far away are you from the mean? It's kind of the average that you're apart from the mean. Okay, that's the best way of describing it, really. It's just what's the measure of dispersion? How far are you away from the means? We have two things. We have variances and we have standard deviation. It's very important to remember the variance is this average distance that you are from the mean. That's the variance. The standard deviation is the square root of the variance. So if you know one, you know the other, right? If you know the square root, if you know the variance, you take the square root and that gives you the standard deviation. If the problem gives you the standard deviation and you need the variance, well, you just square the standard deviation and now you have the variance. So that's a common source of errors, so pay attention to that. Okay, so here we are, section 9.5, and we're going to test the differences between variances. So this is just motivation here. He's trying to tell you, hey, listen, sometimes we're comparing means. Sometimes we're talking about, the means of populations. Sometimes we're talking about proportions. But sometimes we want to know about variances and standard deviations. We want to know, is the variation in the temperatures for a certain month of two cities, are they different? Okay, we'll see examples as we go along. For right now, let's just assume that there's a legitimate reason why we're interested in the variance or interested in the standard deviation. Okay, here's another example here. He wants to say, hey, is there a difference between the variance of cholesterol for men and then compare that cholesterol for women? So there's a test for that. It's called the F test. Now you got to be real careful here. When we say F test, that's not uniquely defined. You have to be very cautious because it's really the F distribution that is used. And you use the F distribution in a variety of contexts. Here's one source of potential error. The F test should not be confused with the chi-square test, because you may recall in the chi-square test back in chapter 8, we were comparing a single sample variance to a specific population variance, and that was in chapter 8. So let me bounce to that to show you that, remind you of that formula. Okay, so this is chapter 8. At the end of the chapter, the little summary they have. So as the summary says, a single variance can be tested by using the chi-square test. So remember, in chapter 8, we're always talking about comparing a sample to the population. That's what it says right here about the variance. And here's the formula. When we were in chapter 8, we were comparing one single variance or standard deviation. We were comparing that to the population standard deviation, and here's the test that we used. So obviously I'm not going to go back and talk about that again, but I just want to compare and contrast. In chapter 8 we use the chi-square test, and we are comparing a sample variance to the population variance. Whereas, give me a second here, in chapter 9, we're always comparing two samples. So you got a sample 1, sample B, men and women, brand A, brand B, boys and girls, whatever it is that you're comparing two samples. You take the medicine, you don't take the medicine. Those are the two samples that you're comparing. You're not comparing them to the original population, okay? You're asking the question, gee, I wonder if these samples represent the original population, or do they represent two different populations? All right, so here we go. The F-test is a family of distributions, or the F distribution is a family of distributions. And here's kind of the gist of it here. If you are taking two independent samples, so they have to be independent, and you're taking them from two normally distributed populations. So you've got a population number 1, population number 2. You are to, and this is a little bit ambiguous here. It says in which the population variances are equal. Well, that's what you're testing. You're testing that concept of, are these two population variances equal or not? So you kind of are assuming that for the null hypothesis. So you're assuming that, and that's what enables you to use this F distribution. The point of the testing is going to be to determine, is it true that they are equal or not? That's always going to be the question, is are the two population variances equal or not? And how do we know? Well, we can't possibly look at the entire populations. That is too hard. So what do? We always take a sample. So given these two samples, can you conclude that the population variances are equal? Or is it so unlikely that you would get these two samples? It is so unlikely that you would get these two sample variances that you reject the null hypothesis. That's always kind of what's in the back of your mind here in this situation. Okay, so here's some characteristics. The values cannot be negative. Okay, well, why is that? Well, a variance is always positive, and what we're going to be seeing here is that F is the sample variance divided by another sample variance. These are both positive numbers, so they can't be negative. It's going to be positively skewed. I'll leave that for the reader. I'm not sure he proves that, but let's just assume that's true. The mean value is approximately equal to 1. Well, why is that? It's approximately equal to 1 because if these guys are random samples from the variances of the population, I didn't say that right. If these samples are taken from the two populations, right, sample 1 and sample 2, and if the variances are approximately equal, then this ratio, this guy on top of this guy, is going to be approximately equal to 1. So that's kind of the intuitive proof of that. It's not a rigorous mathematical proof, but that's the way I look at that. Okay, and it's a family of curves, and it's based on the degrees of freedom. So the degrees of freedom, just like before, are going to be based on the sample size. So it's the degree of freedom, but this one is different. There's going to be a degree of freedom of the numerator, and there's going to be a degree of freedom of the denominator. And the table that we use to come up with our F values will reflect that. So it's unusual, or it's unique. We have never done this one before. We've never done a table like this one before. The way this works is the larger of the two variances is placed in the numerator. So if you have a variance of 20 and a variance of 15, well, the 20 goes on top. If you have 25 and 30, the 30 goes on top. The bigger number always goes on top. It has nothing to do with the sample size. Is only to the issue of the actual numerical value of the variance, which is the bigger guy. The big guy goes on top. So the way I remember this is, it sounds stupid, but this is the way I remember it, is I think of my kids, when they were little kids, who usually won the fight. The guy on top was always the bigger kid. So John was beating the crap out of Jake. Okay, so that's the way I look at it. Okay, the big guy goes on top. All right, the F-test has two values for the degree of freedom, as I mentioned to you. We'll see how that works here in just a little bit, okay? All right, so he says that again here. Okay, so this is, he's talking about table H. How do you do this, okay? Let's take a look at that table. Give me a second here. Okay, so table H is worth a little bit of your time. I want you to, hopefully you follow my advice here. Get your book out and take a look in the back of your book and look at table H. One of the first things you'll notice is that there's more than one table H, okay? This is table H. This is where alpha is equal to 0.005, okay? Let's go to the next one. It looks exactly the same, except alpha is equal to 0.01. So what's going on here is there's too much information to put it on one table. They have to do separate tables. Here's an alpha is equal to 0.025. So you get the idea. We have a separate table for each one of these alphas, okay? Now, here, this is the degree of freedom. This column right here, we're used to that being the degree of freedom. But in this case, for this particular test statistic or this test value that we're using, namely the F value, there are 2 degrees of freedom that are of interest. This is the degree of freedom of the denominator. This is the degree of freedom of the numerator. Okay? All right? So it says right there, numerator. Oops, hold on. Okay, sorry, I had a little technical difficulty. So this is degree of freedom of the numerator, 1, 2, 3, 4, and so forth. This is degree of freedom of the denominator. I apologize if I said that wrong before. And this table is the one that you would use if you're interested in alpha 0.025. You would use the other table, same setup, same format, but on this one, this is for alpha is equal to 0.01. So I think the text actually is going to start talking about one of these, so let's take a look at it. So this is F critical values for alpha 0.005. Okay, it gives it for all these different, these are the tables it's going to give you. 1, 2, 3, 4. There's 4 tables. Oh, 5 tables. There's 5 tables. Each one of those alpha values involves a separate table. The thing to remember is these are one-tailed values. Okay, one-tailed value. Okay, so those tables of values, they're one-tailed values, but wait, we sometimes will have a situation where we're talking about, as an example here in this example, we'll see in a minute, we're talking about a 2-tailed test. So what the heck do? We've got a tail here, we've got a tail here. Well, this is just one of those situations. What you'll see is that we only find the one critical value. There is another critical value, but to be honest, we just kind of ignore it because we don't care what it is. This is the critical value that we're going to be investigating. We're going to find out, does our test value come back greater than this critical value? That's all we care about. So that the table does not include this guy over here, and that's kind of interesting, right? Because before we always knew what that number was. So it's a little different test, a little different table. As I've said before, in real life, everything is done on a computer, but I think it's worth your while to learn how to use these tables. It really helps you understand how these things work, okay? All right, so I've explained what the various tables are. We're going to end this recording, and then we're going to take an example here of how do you use the tables. We got to be able to find these critical values, because it turns out we're going to do these hypothesis tests are going to be done exactly the same way. We state what the hypotheses are, the H sub 0, H sub 1. We write down what it is. Then we find the critical values. We draw our cartoon. Then we find our test value, and we decide, are we or are we not outside the range of acceptable values? Are we in the critical value area? Are we in the reject the null hypothesis area? Exactly the same as we did before. So that's the end of this tape.